So hi again, everyone. So my name is Olivier Grisel. I work as a software, open source software engineer in Probable. I'm primarily focused on the development and maintenance of scikit-learn and related open source projects. So in this presentation, I won't talk too much about scikit-learn or the libraries themselves, but more about mathematical concepts that you might run into when you develop regression models, so predicting a continuous output using a machine learning system. And in this presentation, we will try to see what are and why do we need to maybe in some cases produce prediction intervals rather than just a single predicted value, scalar value. And we will relate this objective to the minimization objective functions of regressors, of machine learning models. So the squared error on one hand, the absolute error in the middle, and the generalization of the absolute error, which we call the pinball loss, that will be very useful for prediction intervals. And once we know how to train the model, we want also to know how to evaluate those models meaningfully, either when we predict the average value of the target variable given the input, or a quantile of the target given the input. And then we will discuss alternative to traditional quantile regressors. And we will show that you can also bin the target variable, quantize it into discrete levels, and treat the problem as a classification problem. And once you output the classification prediction, you can reconvert it back to a quantile regression prediction. So now we will have different ways to do the same thing. And so we will want to contrast with the pros and the cons. And finally, we will also discuss alternatives that I also tried that didn't work, and explain the reasons why they didn't work or why they didn't bring additional value on top of what we already did. And in particular, we'll discuss Bayesian regression and conformal predictions. So why probabilistic regression? So in real life, data is complex, but for this presentation, for educational point of view and to be able to show graphics, I will focus on a single input function, an input value that is continuous, and I want to predict a single target variable that is also continuous. So this is a simplistic case, but it's complex enough because you have this weird relationship that we call heteroscedastic noise, where you see that the difficulty of the prediction task is not the same everywhere in the feature space. And in particular, in that region, between, let's say, x equals 0 and x equals 1, you see that the target value y has a large possibility, a large range of variation that you cannot control just with the information that you have in the input x. The variability of y depends on other things that are not measured via the measurement of the x value. And our goal in traditional regression is, given a value of x, predict the average possible value of y. So this is the gray line in the middle, and this is actually the ground truth of the data generating process for the synthetic data set. And you see that just predicting this expected value of y condition on x is useful on those regions of the feature space. It might be also useful here, but in the middle, it's not the full story. You might want to know that there is a large uncertainty on y in that region of x, which is not the case in other regions. So, as I said, different regions can have different noise levels. I put noise in quotes because noise is not necessarily noise the way you would traditionally think about it intuitively, but noise in the target variable, in the observations of the target variable, is mostly caused by too coarse-grained measurements of x. Like the input features are not precise enough to be able to know the exact value of y. Or maybe you have missing informative features. So instead of one feature, you might need a second feature to be able to precisely predict y. But maybe for a given problem, you cannot have access to that second feature, predictive feature, because of legal reasons or privacy reasons or whatever. And so you have to deal with the limited number of observed variables, and to deal with the uncertainty that results from them. And so in this case, even the best regression models, if you have an infinite number of data points, cannot be perfect everywhere. So it's not the problem of the model, but hyperparameter. It's not the problem of the number of training data points. It's a fundamental problem in the choice of the variable that you have access to. And, or maybe some randomness in the word that you cannot guess because you have limited measurements. So this is what we call heteroscedastic problems, because this is the lack of homogeneity of the noise in the feature space. And it's aleatoric uncertainty, because even if you had access to an infinite data set with the best model, the prediction error will not be zero. There will still be variations around your predictions, or around the average prediction. So what can we do about it? Instead of focusing on just predicting the average, the expected value of y given x, what we can do is train 3 different machine learning models. We can still keep the one that predicts the average value, because it might still be useful. But on top of this, you might want to predict 2 additional values, which are prediction intervals that have statistical guarantees. And a typical statistical guarantee we look for is a coverage guarantee, such that we want, for instance, for the upper prediction here, we want, for instance, to have 90% of 95% of the data point below that dotted line. And for the bottom dashed line, we want 95% above this. And when we manage to do this, then we have meaningful interpretable prediction intervals that gives us information via their widths, that if you have a large orange interval width for a given choice of x here, you know that the prediction is quite uncertain. Whereas if you would do the same in the -2 position for x here, the width of the interval would be very narrow, so you would know that the prediction is very, very confident. So what should I care? It depends. For machine learning pipelines, the prediction can either be consumed by machines, automated systems, or by humans to drive human decisions and to inform human decisions. But in both cases, it might be useful to be able to rely on prediction intervals if they are reliable. So for instance, when the predictions are consumed by machines, a high confidence prediction can be processed automatically. For instance, if you know that the value is above a threshold with a high confidence because the interval doesn't overlap with the threshold, you can take one action, and if it's below and it doesn't overlap with the threshold, you can do another action. And if the prediction interval overlaps with your decision threshold, then maybe you have the choice to defer the decision to either later, once you can collect extra information such that your prediction model is more precise, or maybe defer to a human expert that might be costly, but might be the only way to deal with those complex cases. But at least you will not bother the costly human experts on trivial cases. And to do this distinction, you need the prediction intervals. And so you can also use leverage prediction intervals when the humans take the final decision. They might be meaningful to them, so easy to interpret, and might allow them to take optimal decisions for their internal business objective or personal motivation or objective that is not necessarily well expressed. But if they have access to this extra information, they can do more meaningful actions. For instance, Let's take the example of traffic modeling, a prediction of time to arrival, depending on different navigation systems, such as a public transportation, bike, or a taxi. If there is a lot of traffic, then the time prediction for the taxi might have much wider confidence in prediction intervals than the bike, for instance, and depending on that, you might decide to choose one or the other, or maybe to adjust the time of departure. For instance, I computed in Google Maps, I said that I wanted to go to the Roissy-Charles de Gaulle airport either this morning at 6 o'clock or this afternoon at 6 o'clock in the afternoon. And you see that naturally, in the user interface of Google Maps, you have those prediction intervals, an estimate of the time it's going to take. And here, 1 hour and 20 minutes for the upper bound, you might need to leave much earlier than if you booked a taxi in the morning, if you have to take a flight, for instance. So those are very useful for human decisions also. So how to build those prediction intervals? We can consider different kind of objective functions, the squared error, the absolute error, and the pinball loss. So they are all interesting because when you minimize the squared error, you have traditional least square regression, and in this case, your estimate is the conditional mean, the expected value of y given x. So the prediction in the middle, let's say. Most of the time it's in the center of the interval, but not necessarily exactly. If you minimize what we call the absolute error, then you will estimate the conditional median of y given x, the y given x distribution. So in many situations, the difference between the mean and the median is not necessarily that interesting. What is more interesting is that if you generalize the absolute error to some general version, which is called the pinball loss, with a specific quantile level, then you can estimate any level of the cumulative density function of the y given x distribution. So I represent here all the prediction, the objective functions. So in the x-axis for each of them is the difference between your prediction and the actual observed value. And so if you are at 0, it means that you predicted exactly the observed value. And when you minimize the squared error, mathematically, you will end up with an estimate of the mean of the y given x distribution, median for the absolute error. And then you see this asymmetric pinball loss, asymmetric generalization of the absolute error, that makes it possible to estimate any kind of quantile level. And so here I displayed it for 0.05 quantile and 0.95 quantile. So for a lower prediction and an upper prediction in the interval. So let's do a Newton descent in Google Slides and try to optimize the squared error for a polynomial regression model in my Google Doc. So we take this synthetic data again, and the first task is to minimize the squared error to get an approximation of this gray line from the gray data point by training a model. The first model in our triplet will be what we call a spline transformer followed by a linear regressor, and this linear regressor will minimize the squared error. So it's typically like the ridge regressor in scikit-learn. I just re-implemented it so that we can have a progressive view with a different solver of the intermediate step that might happen under the hood. But here we minimize the squared error on the output for a linear model on features that are polynomial transformation of the original feature. And as a result, we get more expressivity by using this pipeline. So originally, the model predicts 0 everywhere because the coefficient of the last layer in our pipeline is just predicting 0 because of the 0 coefficient. So if you look at the mean squared error of those interesting 5 data points with color triangles here, you see that the ones that are far away from the orange prediction line have a large loss. And if you do the sum of all the loss for all data points, you get this dashed arrow line here on a linear scale. And you get this blue data point here on a log scale. And here we have the number of iterations. So this is at 0 iteration. It's before we start to learn. As soon as we do a few Newton steps, the coefficient of the model will evolve to minimize progressively the average mean squared error. And so you see now, by moving the coefficient in some way such that the prediction function gets closer to the purple triangle and the blue triangle here, you see that they gather around the 0 location of the mean squared error. So here, that was the original one. And if I do one step, they already collide, they group together. And if I continue, in the end, you see that the purple one is actually very close to 0. And now the ones in the extremes are this orange one and this red one. And they are the ones that are driving the remaining loss. And it's not possible to go below this. You see that our orange prediction model has matched the exact theoretical value of the conditional expected value of y. So it's not possible to go below. We still have some non-zero loss because this triangle here is not exactly on the orange line here. This red triangle is not on the orange line. But it's a limitation of the choice of the features. We cannot improve the model in any way. So we can do the same for pinball loss minimization. So instead of one single model, we have a triplet of 3 models, one for the mean and 2 for the upper and lower bound. And so for the lower bound, we will have the quantile loss with quantile 0.05. And for the upper bound, we'll have quantile with 0.95. And we put all our models together in a collection, Python list, for instance, to keep them grouped together. So here I show the same plot, but instead of one model, I will have 3 models. Originally, they all are the same location, but you see that progressively the 3 loss will evolve in different manner. Originally, you see that for the lower prediction, so this is the lower prediction, the blue point is the most annoying. And it's annoying for this model because it wants to be below the majority of the points. So if there are points below its prediction, it doesn't like it at all. So the blue and the red one, they don't like it. But for the upper prediction, they don't care about it much because this prediction wants to be above every data point in the training set. So these points, the purple one and the orange one, are actually the ones dominating the loss. So if we iterate and we do these Newton steps for those 3 different optimization objectives, we get the 3 different coefficients sets for the prediction functions. And progressively, if we iterate a lot, at some point we will converge to something that is very close to the theoretical thing. Here we converge to almost the theoretical distribution quantiles, because we have enough data points and because the features that I did with the spline transformer are rich enough such that the linear model that I fit at the end of the pipeline has the good enough expressivity to deal with it. So we can do the same with gradient boosted trees. So instead of the polynomial regression pipeline, I can use the same loss functions and the same quantile for a triplet of his gradient boosting models in scikit-learn, for instance, or you could do the same with XGBoost or LightGBM or CatBoost. And you have the same kind of convergence, but because of different inductive priors for decision trees, they do not exactly match. The prediction function is not smooth. So for this problem, it looks worse, but in general, it's not a problem in real life when you have many features and categorical features and so on. Typically, decision trees are better. You can also use bin target classification, as I said in the introduction. So it's quite easy to write your own scikit-learn meta estimator that will wrap a base classifier and specify a number of bins, and then bin the target variable y to get classification targets instead of regression targets, and then fit a classifier on the binned version of y. And once you have done this, you can change the prediction function to predict quantiles instead. And so under the hood, you will look at the threshold, what the threshold mean for the binning, compute the probability of belonging to different bins for a given data point, and then do a cumulative sum of the bins in the right, of the probability of belonging on the bins in the right order, and then do some interpolation to recover cumulative density function levels for the quantiles of interest. So yeah, it makes sense mathematically. Maybe the code is very quick to read, but it's not too complex, and it's a very generic thing, and it can work for any kind of classifier, neural network, logistic regression, random forest, decision trees, anything. And you can wrap any pipeline in scikit-learn and do that. And you can see that we get also quite good results. They might not be as smooth at the beginning because it depends on the many hyperparameters and the number of bins and how they interact with the underlying model, but they look quite good anyway. So how to tell which of those models is the best? Here we could plot the prediction function visually because it's just a 1D regression task, but in real life you have many dimensions and you cannot directly plot the prediction functions this way. So instead what you can do is compute metrics. And so for the triplet, we can compute a bunch of metrics, the one for the middle prediction, but I will focus on the prediction interval. So for the prediction interval, you can compute the pinball loss on a test set instead of just the pinball loss value on the training set that is optimized directly by the quantile regression model. You can also use it as an evaluation metric on a test set. So the values are not necessarily intuitive for humans to understand, but lower is better. And so you see that polynomial regression to predict the lower bound is slightly better than the histogram gradient boosted trees or my polynomial regression that has wrapped with my target binning meta-estimator and logistic regression. So, but those two, apparently, they are very similar. For the upper bound, you see that this one is significantly better than the other two. Well, I didn't do cross-validation, so I'm not so sure about this. But I'm pretty sure it is actually, just by looking at the plot. But they are not too far away. And you can also compute the average coverage on the full test set, which means the number of time an observation is between the above and below prediction. And ideally, because we used those quantile levels 0.05 and 0.095, we want 90% of the data point to be between the two, because if you take the difference of the two levels. And so here you see that we are very close, especially for this one, we are very close to the target coverage that we specified in the loss functions. And assuming that we cover our objective, that the coverage matches our objective, what we want is to have on average interval widths that are as small as possible to be as informative as possible. Because if they are too wide, then we can have easily a coverage of 100%, but with very wide interval and a completely useless model. So those metrics are more humanly understandable, but those two are actually proper scoring rules that capture everything you need to know. So yeah, maybe they speak more to statisticians, but they are sufficiently informative in themselves. What we can do on top of those numbers is try to look at a reliability diagram, which is especially useful whenever you deal with probabilistic predictions, classification or regression. But for regression, we can do it both for the conditional mean prediction, so the average least square as we do as usual. So we bin the test set by predicted values. So all the values that are highly predicted, all the data points that have a high prediction are grouped together, all the data points that have a low predictions are grouped together, and then we compute the average observed value within each bin, and we plot it on this diagram. And if we are on the diagonal, it means that we have a well-calibrated model for this target conditional mean expectation. We can do that also for the quantile regression problem. The only difference is that instead of computing the average value within the bin, we will compute the 95% percentile within each bin. And then the perfect model will also be on the diagonal. So you see here, our model is not completely perfect. And we can do it for the lower bound. And we can see that for the lower bound, it's very good, and for the upper bound, it's very good. And the pinball loss is able to assess both calibration and discrimination at the same time. And so the fact that we have a calibration problem here on this reliability diagram is actually visible also on the pinball loss. So I think I'm running a bit out of time, so I will skip the method that don't work. So you see Bayesian ridge on the polynomial features is bad because of misspecified prior. We can also try split conformal predictions on the average prediction, and it's also not able to model heteroscedastic noise, so it's useless, I would say, for this problem. If you want to capture heteroscedastic noise, you can use another conformal prediction from MAPI, which is called CQR. But for our model, it doesn't change anything because the average coverage of the model was already quite good. And the CQR correction is just a correction on the average. So it's not able to correct calibration problems, the remaining calibration problem that we observe. So it doesn't change the model in this case. But it might still be useful on other tasks where you have an average coverage that is not good. Then CQR can help fix that. So some takeaways. You can read them on the slides because we are running out of time. And thank you very much for your attention.
Thank you, Olivier. So we have 4 minutes for questions. Yeah.
Hi, I have a small clarification. We train these prediction intervals in sequence to the initial training, right?
Is it close to the?
I mean, we do the regression of y and x, this posterior, and in sequence to this, after this, we do this prediction interval training, right? Or is it parallel?
Sorry, I didn't understand.
I mean to say, let's say we are training our y and x variable. Y is the labels, x is the
yes, the features. Input.
So we do in parallel to do through this, we do this prediction interval. The layers for the prediction layer we do in parallel, or is it sequence?
I don't understand. We do in what?
Parallel or sequence?
Parallel. Parallel. Okay. So the two models that predict the upper bound and the lower bound, maybe on this one. So this prediction here, which is below actually, and this prediction here, which is the highest, they are computed when you do quantile regression. They can be computed by two independent models. For instance, two different gradient boosted trees. And you can train them independently. So if you want, if you have many machines at your disposal, then you can train them in parallel. But for instance, gradient boosting decision trees can also learn in parallel. They can when they do their splits, they can already use all the cores on your machine. So if you were to parallelize across the models or train the two models sequentially but have the model trained in parallel, from a computational point of view, it wouldn't necessarily make a big difference. But it really depends on which underlying model you use.
And from accuracy point of view?
For
accuracy
point of view, you get the same result. It's just a computational consideration.
Okay. Thanks.
So a bit related to this question is that when we do the bind quantile regressor, so the one where we wrap a classifier, in this case it's a bit different because we have a single model that is trained to predict all the possible quantiles at once. So it's better in a way because it's simpler from an operational point of view to deploy this model. There is just a single artifact to train, to evaluate, and so on. And then you can use to estimate any quantiles because the choice of the quantiles, you can choose at prediction time which quantile you want to estimate. So it's nicer in this way. But the fact that you have independent models for the quantile regression, the traditional quantile regression, might also be a benefit because you can do hyperparameter tuning that is different from the upper and the lower, and sometimes they have not the same complexity. So maybe gradient boosting might be optimal for the upper bound, and polynomial regression might be optimal for the lower bound. So you have more flexibility when you decouple the two models.
Fantastic talk, very relevant, especially to what we are doing every day. And I have a question. In case of zero-inflated data or bimodal data, what strategy do you suggest?
Which kind of data? I didn't know.
Zero-inflated data, so you have many zero values, you are in the positive field.
Okay.
Or bimodal, for instance.
Okay, so for those particular points, so you have only positive values, but many of them are zero. Like in insurance companies, typically, you want to predict the cost of how much you need to refund customers if they have an accident, for instance. And most of them will not have any accidents, so you have not to refund anything. So this is the kind of... so in this case, maybe if you can make assumptions on the target distribution, maybe for this particular case, I think the 2D distribution will be very well suited because it can have a peak at 0 and only positive value otherwise, or Poisson and Gamma compound model or this kind of models might be more beneficial. And then you can have a full distribution of a full estimation of the conditional distribution, and then derive quantiles from them if you want also. But in this case, it's a bit weird because it's more like the sequence of a discrete problem, whether or not you have a 0 or non-zero, and then a continuous non-zero in the cases. So you can treat it as a cascading problem, and that might also be more interpretable because prediction intervals for this kind of very weird distributions might be... so I didn't present it in those slides. I didn't have time to but it's possible in scikit-learn. There is the 2D target for both linear models and for gradient boosted trees, I think. Yes.
Thank you for your talk. You covered mostly the quantile regression methods, and I wonder if you can share your thoughts on model to predict the mean and standard variance. For example, XGBoost with its special loss functions.
The mean and what?
And the standard variance.
Standard variance, okay. So what you could do, if you want to use a quantile regressor to capture more information about your target distribution, so you could use this approach actually, because this, you have the full CDF with the mean target. So you can compute any statistics, no, not statistics, any estimate of your target distribution. You have the ability to compute them. But alternatively, what you can also do is instead of just training 2 quantile regressors, is to train a grid of quantile regressors at 0.01, 0.05, 0.1, and so on. Maybe it's more interesting to have a denser grid around the edges and not as dense in the middle. And then you can interpolate those quantile predictions to recompute other things about your target distribution of interest. So that will be an alternative. Especially if you do neural networks, it might be cheap to do because neural networks can be cheaply have multiple outputs on, even if you predict one single target variable, you have different outputs for different quantile levels. And most of the computation is shared for all those outputs. It's just the last layer that does this, so it's quite cheap to do that for a neural network. I don't have code to show, but I'm pretty sure they can find it or ask LLM to help you do PyTorch code for this. It should be able to do it.
Okay, so we are closing like the session of the morning. If you have more questions, you can find Olivier around and ask directly the questions. So we can give a round of applause.
Thanks.